In this video, we're going to use what we know about integrals to now calculate the volume of a three-dimensional object. So first I want to remember the definition of a definite integral. So remember when we're calculating this definite integral, what we're really doing is we're adding together an infinite amount of rectangles. And so here we're calculating the length times the width. If we look at our actual integral, this here calculates the length because it's the height of each rectangle. And this, remember, is some really, really small change in x. So that's the width because, remember, they're very, very thin. So what it kind of ends up doing, as we can think about, is this is going to add together all of the y values, which is just like how long the line is. So if I wanted to find the area under this curve here in this graph from, let's say, I don't know, 1 to 3. I could add together the length of each of these. And again, they're so thin that we can think of them as lines or very, very thin rectangles. And so that's kind of what we think of when we're calculating area. But I really like this idea of kind of looking at maybe a slice of this as just being a single line. What we're going to do now is we're going to take this region, so maybe even the area now from 0 to 4. And if we took this region, we can actually revolve it around an axis to create this three-dimensional object you see below. And then we can use an integral to also find the volume of this object. So I want to show you a video real quick to explain that. So you can see in this video, I have the region graphed. And if you notice, they're now revolving it around the x-axis, and it creates this circular, almost kind of like a funnel shape. And so you can see here again. And so now when we take our cross section, it's actually a circle or a very, very thin cylinder. And you can see here, they're showing you what that cross section would look like. And it started over, of course, but right here, we can see what this cross section will look like. And so what we're going to do is we're going to calculate the area of this very, very thin circle. And then when we integrate it, it's going to add all these together, or basically stack them on top of one another to create the volume of this three-dimensional object. So going back to the notes, you can kind of see that I've tried to illustrate out what each of these would look like. And so again, we can think of them as circles, or we can think of them as super, super thin cylinders. So the way we calculate the area of a circle is pi r squared. And what we want to do is we want to add all of those together. So that's what the integral is going to do. And then when we put this dx out at the end, remember this multiplies by some super, super small thickness. So again, that's going to be like the height of our cylinder. So that's all volume is. It's area times the height. And so that's why this is creating volume, because it's adding together all of the areas of the circles. And then our formula is actually going to have this pi in the front because it's a constant. And so on the next page, you can see that if anytime we want to find volume, as long as we see this word revolution or revolve or rotate or something that implies a circular motion, we're going to use the area formula of a circle, which is pi r squared. We're going to add them together from wherever they begin to wherever they end. If our region is rotated around the y-axis, it's going to look slightly different, but very similar. Okay? So let me get this video set up. So you can see here now, I have a region that's going to be revolved around the y-axis. And again, this is just going to be slightly different because now our circles are going to be horizontal in shape, and you can see this cross section here. And so I'm going to calculate the area using a horizontal distance instead of a vertical distance. But the overall idea is the same. So going back to our notes, and that's all this says right here. Okay, so for example 1, I already have the region drawn out. So all I did was graph this, and it just wants us to take this triangular region, and it wants us to revolve, so that's how we know we're forming circles, about the x-axis. So that means I'm gonna take this shape and I'm gonna revolve it so I have this kind of circular cone shape, and you can kind of see what that looks like. So if I were to look at one of these circles, if I were to calculate the area, remember the area is pi r squared. But my radius here is not always the same. You can see the radius of this circle is much smaller than the radius here. And again, we have an infinite amount of them. So rather than using a number, we're going to use an equation. And the equation here is going to be whatever the function is minus 0. This is going to give me the radius of each of those circles. And so my function is negative x plus 1. And so that's what I'm going to use as my radius. So pi times that radius squared is what I'm going to add together. And I can look to see that my very first circle starts here at 0. And I'm going to add them all the way until I get to my last one here at 1. So from 0 to 1. And again, if I have x's in the problem, then both of these need to be x values from left and right. And we're not actually going to evaluate this, but this is how we would go ahead and calculate it. And so remember, just to do this, we would have to FOIL this before we could actually integrate. Okay, for our next example, we're revolving the region bounded by a quadratic function around a line rather than an axis. So here, again, we see this word revolve. That's how we know we're making the circular shape. And this is our axis of rotation. So we can kind of even make like a mirror image to try to see what this revolved shape will look like. And I like to draw these circles just so that I know what one of those slices look like, because all I need to do is find the area of one of these. And then when I integrate it, that's going to stack all these on top of one another and create that volume. So for one of these circles, my radius is top minus bottom. Remember, that's how we calculate vertical distance. So the top here is always on this quadratic function. So I'm actually going to use function notation here. So I'm going to say we're going to take f of x, and we're going to minus every point on this blue line. Well, we can see this is always equal to 1. So we could use 1, or we could call that g of x. I'm going to go ahead and call it g of x, just to be consistent with my function notation. And that calculates the radius of each of these individual circular cross sections. So to turn it into area, I need to do pi times this radius squared. I'm respecting x. And I can come back over here to my picture and see that my first circle starts here where they cross, and my last circle is going to be out here where they cross. So I do need to figure out where these two cross. And just like before, we're going to find that by setting the functions equal to one another. So 2 minus x squared, I want to know when that's equal to 1. If I solve this, I can subtract 1 to the other side, or I can take everything to the right just to make it positive. Maybe I'll do that. So we'll get positive x squared minus 1. And if we factor, we'll get x plus 1, x minus 1, and we'll see that our solutions are plus or minus 1. So if this is negative 1 and this is positive 1, those are going to be my bounds. And this is how I would calculate the volume of this three-dimensional, maybe kind of like a football object here that we see. And that's going to be it for this video.